In this lecture, we'll discuss how to visualize convolution that is given by this integral over here. So convolution of two functions f and g, let's say in time domain, is given by this integral f of tau multiplied by g of t minus tau and integral over tau from minus infinity to infinity. And we've seen in the previous lecture that this operation is called the convolution. And we've also seen that the Fourier transform of convolution of two functions is simply the product of the Fourier transforms of those two functions. And also we have seen that the Fourier transform of the product of two functions in time domain is equal to 1 over 2 pi times the convolution of the Fourier transforms of the functions f and g. That means convolution in time domain is equivalent to multiplication in frequency domain, and multiplication in time domain is equivalent to convolution in frequency domain. So the convolution operation is used in numerous ways in experimental science, and we'll discuss the applications of convolution as we proceed in this series of lectures. And among all these applications, the most intuitive way of visualizing the convolution operation is to think of it as using one function, let's say g of t, to smooth and average another function, let's say f of t. So convolution can be thought of as smoothing and averaging operation. To see why this is the case, let us consider convolution of two functions f and g in time domain. Let us say that we have this function f of t that is some noisy signal that consists of some true signal with overriding random noise. So let's say that the signal is something like this. And we want to perform convolution of this function with another function, that is g of t. And for the purpose of smoothing and averaging, we can consider a function that has a unit area, so that when we do this convolution operation, the function f of t does not change in the amplitude. Let's consider a general function which is not symmetric. So this is my function g of t, and we want to perform convolution of the function f of t with this function g of t. So the convolution of f and g is given by this integral f of tau times g of t minus tau d tau. So note that in the integration we have f and g as function of tau. So we can replace this t with tau, because we have in this definition of convolution the functions f and g are functions of tau. So if you look at this term over here, what we have is g of t minus tau. That also means that this is g of minus tau minus t. So essentially what we have is that we take this function f of tau over here and multiply with this function g of t minus tau. So g of t minus tau can be thought of as this. So first we flip this function g like this. So this is my function g of minus tau, and then I translate this flipped function, let's say by time t, and I'll get this function like this, and this is my function g of t minus tau. So g of t minus tau means I flip my function g and then translate it by a time t. Then if you look at this term in convolution, next step is to take product of this function f and this function g of t minus tau, that is the function g that has been flipped and translated by a time t. So if we plot this term f of tau times g of t minus tau, we'll have product of these two functions over here and here. So the product will take on non-zero values only in the region where g of t minus tau is non-zero. The next step in the convolution operation is that we take this product f of tau and g of t minus tau for a particular value of t, and then we integrate it over tau. That means we find the area under this curve, that is the product of f and the flipped and translated function g. And this area under this curve over here will give me a single value of the convolution of f and g at a particular time t, and let's say this value is this particular value, and we'll repeat this process for different values of time t, that is the time by which this function g that has been flipped is translated. So at a later time you'll have this function something like this that has been translated to a different time over here, and then we'll again have the product of f and g at a later time, which will look something like this, and then we'll again perform this integration and we'll get the area under this curve, and that would be another point over here. So in this way, if we do this operation that we flip the function g and then we translate this function after flipping, so from g of tau we flip it to get g of minus tau, then we translate it by a time t, so we have g of t minus tau. After translating, we multiply f of tau with g of t minus tau, and after multiplication we integrate and then we get a single point at a particular time t. So this coordinate is t and not tau as all the above three plots. If we do this convolution procedure, that means we flip, translate, multiply and integrate, we'll get a curve that is a smoother version of the function f of t. Again, to understand how the convolution works is that you flip the function g, and once you have flipped that function, you keep on translating that function for different values of time t, and then after translating that function to a particular value of t, you multiply it with the function f of tau, and the resulting function is integrated to get a single value of convolution at that particular value of t. And if you do this whole process, you end up smoothing the curve f of t. So convolution can therefore be thought as a multiple repetition of shift, multiply and integrate operation. Of course, by flipping one of the function for the first time before translating or shifting it. So to understand why convolution leads to the smoothing of this function f, there are two ways to think about this. First is by looking at the convolution operation that is in time domain. So consider that you take convolution at two times. Let's say once at this particular time t and another at a neighboring time, let's say t prime. As we have seen that convolution involves weighted sum of the neighboring values of this function over here. So this is what we add up or integrate, and we take a weighted average of the values of the function f of t, and using this weight, that is this g of t minus tau, to get a single value over here. So similarly, if we do this weighted average at a nearby point over here, that is t prime, then what we'll have is that the value of this convolution at this particular time t prime would have some contribution from the values of the function at the time t, because we are taking the weighted average of the values of this function at nearby points. So the value of f of t would be included in this convolution of f and g at this particular time t prime. So what that means is that compared with my original function, that is f of t, if I look at the convolution, because I am taking the mean or weighted average of nearby points, it is more likely that the convolution of f and g at time t and t prime would be closer to each other than the values of the function at, let's say, time t and time t prime, because the value of f of t would influence the value of the convolution at time t prime, and vice versa. We are more likely to have that these values of convolution at time t and t prime are closer to each other than the values of the original function at times t and t prime. So this is how you can make sense of the convolution operation as a smoothing and averaging operation. The smoothing effect of convolution can be better understood if we look at this convolution operation in frequency domain. That is, we've already seen that the convolution in time domain is equivalent to multiplication in frequency domain. So now if we look in frequency domain, understanding convolution is easier because we can simply look at the product of the Fourier transforms of the functions f and g, and that if we take the inverse Fourier transform, we'll get the convolution. So it is easier to understand convolution in frequency domain. Imagine that this function has a Fourier transform with a magnitude given by this. So this is my magnitude of f of omega. Essentially what we have is we have some frequencies in this spectrum which might correspond to the true signal, and there are many other higher frequencies that correspond to the noise. Now let's say the Fourier transform of the function g looks something like this. Then the product of the Fourier transforms of f and g would be non-zero only in the range of frequencies where g of omega is non-zero, and then we'll take product of f of omega and g of omega, and we might get a resulting product something like this. So the idea is that the frequencies over here that are higher in magnitude are zeroed out due to multiplication with the Fourier transform of this function g. So the resulting product f omega times g omega does not have high frequencies. So now if we look at the inverse Fourier transform of the product of the Fourier transforms of f and g, we can clearly see that high frequencies are not present, and therefore if we look at the product of the Fourier transforms of f and g in time domain, that is, we take the inverse Fourier transform, we'll have a signal which will not have high frequencies, and that means that I'll have a smoother function compared with my original signal f of t. So this description of the convolution operation in time domain as multiplication in frequency domain shows that convolution has to do something with the filtering, because essentially when we do multiplication of the Fourier transform of f and g, that is in frequency domain, then we are removing the high frequencies, and by high we mean frequencies that have higher magnitude. So you can have negative frequencies that have higher magnitude, and of course the positive frequencies. So multiplication in frequency domain gets rid of the high frequencies, and therefore we end up in a smoother signal. So convolution can be thought of as a filtering operation where you remove a certain set of frequencies by multiplication of the Fourier transform of the original signal with the Fourier transform of another signal such as g of omega in this particular case. So let us look at some more demonstrations of this convolution operation. And I suggest that there are plenty of good convolution demos on the internet, and I've chosen one, and the link is provided in the description. So what you see in this particular demo is that we have two functions, f of t and h of t. So f of t is shown in the blue color over here, and h of t is this function in the red color. So let's see how the convolution of these two functions is computed. So in this demo, what we can do is that we'll fix this function f of t, and then we'll flip and translate this function h of t. In this demo, you can slide and see how the function f of t and h of t after flipping and translating overlap with each other. So let's look at this particular point. So we have this function which looks like an exponential decay, that is h of t. So in convolution of this function h of t with this blue colored function, the step function f of t. So the first step is to flip this function h of t, and you get this flipped function, and now you translate this function and take the product of that translated function with the function f of t. So at this particular time t, these two functions do not overlap, as you can see in the second plot over here. At a later time, these two functions f of t and the flipped and the translated function h overlap over this particular region, and that is shown in the pink color, and that part of the product of functions f and h are integrated, and you get a single value shown by the black dot in the third plot. So if you keep on repeating this process, instead of having this step function f of t, this convolution operation leads to a smoother step, as you can see in the third plot over here. As we have already seen that convolution of this step function with another function actually leads to this smoothing of this function, and therefore we have this smoother step. So another example and that you can try out with this demo is this, where we take convolution of a triangle pulse with a rectangular pulse. So again, what we'll see is that when we translate and multiply the rectangular pulse with a triangular pulse and then integrate to get a value at a point at the time for which that pulse has been translated, and you do it for all times, you will get a smoother triangular pulse. So this example again shows that convolution can be thought of as a smoothing and an averaging operation. So here we started out with a sharp triangular pulse and we ended up with a smoother pulse over here after the convolution. So a common example of the smoothing and averaging effect of convolution in experimental science is that of the moving average, and which is also called the running average. And this procedure is used to denoise, or what we can say is to filter a signal. The running average or the moving average procedure is relatively straightforward. So the idea is that imagine that you have the value or you have signal at particular points. In practice, we'll have signal at discrete times. Then the basic version of a moving average is that instead of using this value of the function, what you do is you take the value of the function at the neighboring times. So let's say this time is ti, so you can get the average value or filtered value of the function at this particular time t by taking sum of the values of that function at the neighboring points and then taking the average of that. So if you take 5 points, so including, let's say, t of I minus 2 plus f of ti minus 1 plus f of ti plus f of ti plus 1 plus f of ti plus 2 and divided by 5. Then what you've done is that you've taken the values of the function f of t and 4 neighboring points, and then you have taken the average of that. And if you do this procedure, you will see that you will end up in a smoother signal compared with the original signal, and this operation is called the moving average. So the idea is that you move to a particular point and take the average of the neighboring values of that function, and you get a newer value of this function. So why this procedure of moving average leads to the filtering of the signal or denoising of the signal can be easily shown by looking at this operation as a convolution operation. In practice, this procedure is usually done on a discrete time signal, but the basic principle can be understood in a continuous time context. So, to understand this, consider that I have this function f of t that has some noise. Then this moving average can be considered as convolution of this function f with a rectangular pulse, and this is my function g that has been translated to a particular time t. So then we can write this as f of tau, and this function has been shifted by a time t. So if we take product of f of tau and g of t minus tau, we are left with only this part of the function over here, and if we take the area or integrate, we'll get the area under this portion of the signal. Therefore, the moving average can be thought of as convolution of the signal with a rectangular pulse of a particular width. So in the frequency domain, this convolution operation is the product of the Fourier transform of this function f and the Fourier transform of this rectangular pulse. So let's say again that the Fourier transform of f has this high frequency noise, and that high frequency noise is also on the left hand side, and we already know that the Fourier transform of a rectangular pulse is a sinc function. So if we take the product f of omega times g of omega, these high frequency content will be removed because sinc function takes on very small values for high values of frequency, and we'll be left with only this part of the spectrum. Of course, that is modified due to the product with this Fourier transform, and then we'll end up in smoothing our function because we'll not have the high frequencies anymore. So this animation shows how this convolution operation leads to smoothing of this function. So here my signal is shown in blue color and the rectangular pulse is shown in the red color. So the convolution operation involves first flipping this rectangular pulse, and because rectangular pulse is anyway symmetric, the shape remains the same, and then we shift the rectangular pulse to a particular time t and multiply my function f and this rectangular pulse, resulting signal after the product of the original signal and the translated pulse is shown in the second plot, and then the resulting function is integrated to get a particular value. And the same procedure, if we repeat for different translations of this rectangular pulse, we end up in a smoother curve. And all this is because when we multiply the Fourier transform of the function f of omega with the Fourier transform of the rectangular pulse, that is the sinc function, then the high frequencies are removed because the sinc function takes on small values or zero values at high frequencies. So multiplication in frequency domain gets rid of the high frequencies, provided we multiply with a Fourier transform of a function which has zero values or small values at high frequencies, and then we get rid of the high frequencies, ending up in a smooth function. Now recall that from the uncertainty principle, if the duration of the rectangular pulse is small, then the bandwidth will be higher. That means the Fourier transform of a rectangular pulse that is very narrow the Fourier transform of this would be broad, and Fourier transform of a broader pulse would be narrow. So if we convolve our function f of t with a pulse that is narrow, then we would be multiplying the Fourier transform of this function f of t with a sinc function that is broader. That means some range of high frequencies would not be zeroed out because Fourier transform of the rectangular pulse is now broader, and therefore the resulting signal would not be as smooth as one would get using a rectangular pulse having a larger pulse duration. In other words, if we take moving average with lesser number of neighboring points, that would mean that we are convolving the function f with a rectangular pulse with smaller pulse duration, and therefore we will not be able to remove the high frequencies completely because we are taking the product of the Fourier transform of the noisy signal with the sinc function that is broader, and therefore we will still retain some high frequencies, and this is shown in this animation. So compared with the previous animation, here we see that the duration of the rectangular pulse is small, and therefore during the convolution operation, although there is some amount of smoothing, but there's still some noise left because now the pulse duration is small enough that some of the high frequencies are not completely removed. I hope with this lecture now it is clear that the convolution operation can be thought of as a smoothing and an averaging operation where one function acts on the other function to smooth the function.